Sorry, I didn't realize that I was on mute. I'm very sorry. I was I was speaking for the last 2 minutes. Very sorry. Okay, so what I was saying is that those of you who are joining this call, please make sure you're joining using your institute ID for joining the call. If you use your personal Gmail ID and so on, then it asks for permission every time to let you in. Okay, so my suggestion is to use the institute email ID to join these calls. Okay, so is my screen visible and my voice is audible?
Yes, sir.
Okay, thank you. So what we have here are what are called intensity, duration, frequency curves, IDF curves. Very significant and important for planning purposes, for managing water resources and so on. Okay, so the two versions of the same type of curve. Okay, so let's look at the one on the left, where I have on the x-axis the return period of a particular storm. On the y-axis, I have the maximum intensity of a storm of a given return period. And then I have different curves corresponding to different durations of rainfall events, right? So let us look at the outermost curve here. And one trend that we can see immediately is that for all of these curves, as the x-axis increases, the maximum intensity is also increasing, right? So as I move from left to right, the maximum intensity is increasing as the return period is increasing. Now, just take a look at any one of those curves. Let us say there is a 30-minute storm, okay, happening at a particular location, okay. So when a 30-minute storm with a return period of 10 years, what does return period of 10 years mean? A return period means how likely such a storm will happen at that location. What is the likelihood of such a storm happening? A storm with a return period of 10 years means it will happen once in 10 years, okay. It is a probability, doesn't mean it will definitely happen. The probability of it happening is high, right? So a return period of 10 years means a storm of a certain intensity that happens once in 10 years, okay. For the same duration, as I increase my return period, okay, so let us say this is close to 10 years, okay, so it's about 20 centimeters per hour for a 30-minute duration storm. And then for the same duration, 30 minutes, if I look at a 100-year return period, right, which means a storm that happens once in 100 years, that's about 45 centimeters per hour. Does that make sense? What this means is, as the return period of the storm increases, it means the event that is happening is more and more rare, right? So something that happens once in 10 years will have a lower intensity. Something that happens once in 100 years or once in 500 years will have a higher intensity. Does that make sense? Make sense? No? Netik, can you tell us if that makes sense?
Yes, sir.
It makes sense to you?
Because yes, sir. The high intensity storm will not be very frequent.
Hmm.
So the return period is fine, and
Okay. Anybody for whom it doesn't make sense? I guess it's the other way that's more important. If it makes sense, no issues. If it doesn't make sense, can anybody just unmute yourself briefly and ask me why something is happening, or if it doesn't make sense to you, want me to explain again or whatever? Okay, so let's assume that it is making sense for everybody. Okay, so that's the first point. And this pattern is evident not only for a 30-minute duration storm, it is the same pattern continues for a 1 hour duration, for a 2 hour duration, for a 4 hour duration. What I mean is the value for a smaller return period on any of these curves as my point, right? So for a smaller return period, the intensity is, let's say, 12 centimeters per hour. For a higher return period, the intensity is, let's say, 30 centimeters per hour. So in all of these curves, 30 minute, 1 hour, 2 hour, 4 hours, whatever it may be, as the return period increases, the intensity, maximum intensity increases. Now that makes sense. Now the second thing I'm going to do is I'm going to draw a vertical line for any given return period. Okay. And now what this is telling me is that for storms of different durations, as the duration increases, right, this arrow is pointing in the direction of increasing duration, right? The topmost is a small duration, 30 minutes. The next one is a 1 hour duration. The next one is 2 hours. The next one is 4 hours, right? For the same return period, I've drawn a perpendicular line, a vertical line, perpendicular to the x-axis. This is indicating that for as the duration of the storm increases, the maximum intensity decreases for the same return period. Does that make sense? Now, this would be true wherever I drew the line. Wherever I draw this vertical line, I can draw it at 20 years, I can draw it at 50 years, I can draw it at 200 years. Wherever I draw it, this pattern will be the same given the shape of this curve. Does this make sense? What does this mean? It means that as the duration of the storm increases, the intensity of maximum intensity of rainfall will decrease, which means that if I have a very short duration rainfall event, I can have a very high intensity of rainfall. But if my duration of rainfall event becomes longer and longer and longer, then the intensity of rainfall is likely to be lower. Which is to say that suppose sometimes, it's raining the whole day, but during that entire day for some 10 minutes or some 15 minutes, the intensity will be very high, but rest of the day it will be relatively low. Right? You might notice that. Or it will rain very heavily for half an hour and then it will stop, and then again it will continue raining for for another 1 hour or 2 hours or 3 hours, but during that time it will rain at a steady rate which is lower than that smaller duration, right? So a very high intensity rainfall is likely to be of a shorter duration. As the duration of rainfall increases, the intensity is likely to be smaller. That's just the way it works. Okay, so that's what these curves are telling us. Now, why is all this important? Why are these curves important? Now, the same curve has been represented in a slightly different format. The y-axis remains the same, maximum intensity, the one on the right. And then instead of having different durations as the different curves, here I have different durations on the x-axis, and the different return periods are represented by different curves. Okay, it's the same logic. Now, I want you to look at the second curve and use the same logic and try to understand why for a same return period, as the duration of storm increases, the maximum intensity is decreasing. Try to logically understand why that is, and then do the same thing. Draw a perpendicular line, a vertical line perpendicular to the x-axis at any point, and try to understand why uh, the intensity is changing as a function of return period. Does it make sense to you, or does it is it counterintuitive or something like that? Okay, if you spend some time and look at it carefully enough, you'll understand what's going on in each of these cases. Okay, so but then we'll come back to the bigger question: why is this curve important? Why is it important to know this IDF curve? Can anybody think of one concrete example or concrete application where we can use this intensity, duration, frequency curve? Anybody? Okay, let me give a hint. Let us say we are in the process of designing and building a dam. Okay, at a certain location, I want to design a dam. Now, when I want to build a dam, keep in mind that I will typically try to build a dam for a long duration. I'm not going to build a dam that is going to have a design life of 10 years or 15 years. A dam might have a design life of 100 years, right? Or maybe even more. So if I want to build a structure that has to last for a long time, then I need to know how tall must that dam be. And if I want to know how tall that dam needs to be, I need to know how much runoff is going to be generated by that particular river at that particular location, for which I need to know what kind of rainfall will this region receive, right? If I get a once in a 100-year rainfall event, will this dam be able to sustain, right? If I get a once in a 100-year rainfall event of 4-hour duration or 10-hour duration or 24-hour duration, whatever it may be, that will generate a lot of runoff. And that runoff has to be, the dam has to have sufficient height to store all of that water, right? Or to manage that water, right? So that is the idea behind these intensity, duration, frequency curves, or the previous curve that we spoke about, the depth, area, duration, DAD curves. All of these, what they're trying to do is trying to estimate, if so much rainfall is produced, then what will be the impact in terms of the runoff or the stream flow that is generated. Okay, so that is one of the significant aspects of precipitation. We understand precipitation not just for the purpose of precipitation itself, but because it is the precipitation that becomes runoff, which has to be managed, right? So you must have been seeing in the news all over the country, different parts of India. Delhi is getting flooded, Mumbai is getting flooded, Hyderabad is getting flooded, Bangalore is getting flooded, Chennai is getting flooded, the whole country is getting flooded. So we need to be able to make sure that our urban infrastructure is able to handle the kinds of storms that we are receiving, right? With climate change uh, increasing the intensities of rainfall events, right? So you get a lot of rainfall in a short time. Now, for if your urban infrastructure has to be able to handle it, you need to know what is the likelihood of a certain massive rainfall event happening, and then how to handle it if it happens. So what should be the size of your drainage sewers in the urban areas, and so on and so forth, right? So all of these things have to go into the planning of the urban areas, right? So I mean, it sounds a little dramatic if I say it, but it's the truth, right? So if India has to have infrastructure that can handle these kinds of events that are going to come in the next few years, right? With climate change and all of these things, and rapid urbanization and all of this happening, then the only way it's possible is if we have the engineers and the planners who are able to plan and implement solutions for these. And who are those planners and engineers going to be? You guys, right? I mean, you might not be the guy building it, but you can be the person who's planning for it, right? And so on. So I think it's a very interesting area of work, where if you have expertise in being able to predict um, extreme events, then it becomes very valuable in planning our infrastructure in such a way that we can handle those extreme events. Now, it's not just um, um, urban planning where this ability to predict extreme events is important. It's also important if you think about it from the point of view of, let's say, flood insurance. Now, it's becoming a big thing, right? So uh, if you work for an insurance company, and they have to they have to they have to keep the premium. So if your house is going to get affected by a flood, right? So they need to know which parts of the city are more likely to get flooded, right? And then what is the likelihood that flooding might happen in the next 5 years, in the next 10 years, in the next 20 years. So accordingly, the insurance company will have to uh, uh, choose the correct premium amount. Everybody knows how insurance works, right? 100 people pay premium, but only 3 people or 5 people or 10 people actually claim, because only a small percentage of the population will actually get affected, right? That's supposed to be the logic of insurance. Everybody has a risk of getting affected, and then but only a small portion of people who are at risk will actually get affected, and then they'll file the claim, and then the insurance company has to give them some whatever, they'll get some they'll get some compensation in terms of insurance and so on, right? So these kinds of things are going to be more and more happening in the country. Whenever real estate values are going up, and one of the factors that goes into all of this is the insurance calculations and so on and so forth. So it is a very interesting area, right? So whether you're going to go into banking and insurance and so on, or you're going to be a urban planner and whatever it is, right? These ideas are going to be very, very interesting, very important, and very relevant, right? So pay attention. That's what I'm trying to say. Okay. All right. So we're done with precipitation. We are now going to move on to the next module, next chapter. Now that's called abstractions from precipitation. Okay. So now already we are using a fancy word, abstraction. We'll just try to understand what that means. Okay. So as I was saying, runoff, the runoff produced by precipitation is the most important aspect of most hydrological studies. You want to know, I received so much rainfall, how much runoff will be produced. That seems to be the most interesting or most major aspect of most hydrological studies, right? So, but before this runoff is generated, several losses have to take place, right? So if I get 1 centimeter of rainfall, all that rainfall is not going to become runoff. Okay. Before that happens, there are going to be several losses. Okay. Now these losses are referred to technically as abstractions. Okay. So what are these abstractions? So let's just go through the list of different abstractions that take place before runoff is generated. Okay, so you have to keep this in mind. All of this is happening before runoff. Okay, number one, interception. You've already heard what this phrase interception means. It is, let's say I have a tree, right, and rainfall is falling from above, right, and this is my land surface. Okay, so wherever there's a tree, here the raindrops will come and fall on the surface on both sides of the tree, but right at the location where the tree is present, the leaves are going to act as some kind of a barrier, and they will intercept the rainfall before it hits the ground. Okay, so that's one thing that can happen, interception. Then the next thing that happens is, suppose I have, okay, I drew this surface too casually, I have to be a little bit more careful. Let me do that. Let us say the land surface has got these little depressions, right? So what happens is, when this rainfall falls on the ground, uh, instantaneously these little depressions that are on the surface of the ground, these will start getting filled up. Little puddles of water will start forming all over the place. Okay, some of them can be small, some of them will be a little bit bigger, whatever it is, right? So you will have these little puddles of water formed all over the place, and that we refer to as interception, sorry, depression storage. So interception is over here, interception, and then these little depressions which are going to store water is going to be depression storage. Okay, remember what runoff is. Runoff is the portion of water that is going to flow on the surface of the land. Okay, so it's going to start flowing depending on the slope direction and so on. It will just flow on the over the land surface. Now this water that is present in these puddles, it's never going to flow, right? It's always going to remain in the puddles. Even after the rain stops, if you go and look outside, water will flow for some time and then it will stop. But wherever the puddles are there, those puddles are still going to remain, right? So that depression storage water never becomes a part of runoff unless you go and pump it out or whatever, something like that happens. Unless there is some intervention from human beings, that water that's in the depression storage will never become a part of runoff, right? Okay, what is something else that happens before runoff? Interception is one. I've already shown that to you. I've just shown one tree. Imagine hundreds and hundreds and thousands of trees or buildings, whatever. Any obstruction that prevents the raindrop from hitting the land surface, you can think of it as interception. The most predominant one is trees, but there's other types of interception also, like you have buildings and so on, right? Okay, and then this depression. Okay, anything else that does not become runoff?
Sir, infiltration maybe.
Okay, yeah, infiltration. It's very good. So some water will infiltrate into the ground. Infiltration. Okay, so that's the next abstraction. So these are the different abstractions. Okay, interception, depression storage, infiltration. Anything else anybody can think of? Anything else? Anybody? Actually, there isn't anything more. Okay, so you have interception and depression storage, and then you have infiltration. Now again, within these three, there is a further subdivision of these abstractions. So interception and depression storage are sometimes also referred to as initial loss, right? It's referred to as initial loss, the portion of water that is initially lost from becoming a part of runoff. Okay, and then infiltration is also sometimes referred to as the major abstraction, right? Suppose 1 centimeter of rainfall falls on the ground, falls at a particular location, maybe 2% of that, or maybe 1% or whatever it is, becomes interception. Maybe another 1 or 2% may become depression storage. So far, I've only lost about maybe 4 or 5% of water. Okay, and then infiltration may contribute to, depending on other factors, maybe another 5 to 10% might be lost in the form of infiltration. So I got 1 centimeter of rainfall, about 10% became infiltration, about 5% went from interception and depression storage combined, so around 15%. Okay, so the remaining 85% will become runoff. Okay, so that's I mean, I'm just giving you rough numbers. Don't take it very seriously, but that just to give you a idea of the general magnitude of these different terms. Of course, depending on the type of soil, type of trees, the number of trees, the density of trees, the types of trees, because the leaves are also different depending on the rainfall intensity and so on and so forth. So many different factors play a role. The percentages can vary, but I'm just giving you a typical example where about 15 to 20% is the abstraction, and the remaining 80 or 85% becomes the the runoff. Okay, all right. So now let's try to understand each of these terms one by one. Okay, so interception is the first one that we're going to look at. So what happens to interception? The water that gets retained by the vegetation, it may just evaporate back into the atmosphere, right? So if, let us say, I'm just going to exaggerate and draw a leaf. Okay, let's say I have a leaf, something like this, and then there are some drops of water on the leaf after the rainfall event, right? One thing that can happen to to these drops of water that are sticking on the leaf is that they can just evaporate back into the atmosphere, and that phenomenon is called interception loss. Okay, that can happen. What else can happen? Let us say the rainfall happened for 1 hour. At the end of 1 hour, there are these different drops of water that are on the leaf. Some of those drops of water can evaporate back into the atmosphere, and I'm going to call that interception loss. Is there anything else that can happen?
So water can be absorbed by the roots or the some parts of the plant, like some kind of loss like that.
It's on the leaf. Right now, it's on the
Um,
leaf. Just imagine what are the things that can happen uh, to that water that's right now. I mean, I've just drawn one leaf. Imagine hundreds of leaves on a tree. and each leaf having some 10, 20, 30 drops of water. Some of those drops of water can evaporate back. I've already given you one idea. What other things can happen? Okay, one of you can, maybe you can take your friend and make your friend stand under the tree and go and shake the tree, and then all those drops of water will fall on your friend. Maybe that's a joke that you can play. That's something that might happen. That's possible, right? But not every tree is so lucky to have you go there and shake it, right? Most of the trees don't have anybody going there and shaking them, because there's hundreds and hundred thousands of trees in any given area, right? So what else can happen?
A strong wind can shake the tree and the drops might fall.
Yeah, so that's one thing that can happen. The water can just drip off the leaves and fall on the ground, right? When they fall on the ground, they can join the runoff that's happening. These water droplets that are on the leaves can drip off the leaves because of, as he said, maybe if there's a wind blowing, that might cause that to happen, or if there's a monkey jumping from one tree to the other. Okay, that can cause it, or just generally some two or three drops will join small drops will join and become big drops, and when they become big, they become heavy. The leaf kind of droops down, and then the water drops just fall off. Now that process is called through fall. Okay, the water droplets that are on the leaf can evaporate back. That's interception loss. They can drip off the leaves and fall on the ground, join the runoff, and that process is called through fall. And another process is that these drops can run along the leaves and branches, and then down the stem of the tree, and then that process is referred to as stem flow. Okay, so these things can happen, right? So, I mean, you might be wondering, is this such an important deal? Why are you complicating it so much? Well, it is important, right? If you are interested in figuring out, if it's only one tree, it's okay, it doesn't matter. But imagine if in my area, I'm interested in a particular area, imagine there are thousands and thousands of trees, and then I get some rainfall, then how those trees behave determines how much runoff will happen, right? And if this is what is happening at each tree, then the combined effect of thousands of trees, it's going to play a major role. Okay, if it's an urban area, I don't have too many trees, then maybe it's not a big deal. But if it's a forested area over which this rainfall is happening, then all of these processes that we're talking about, they might have a very big role to play in what happens to that rainfall. Okay, so we have to be very careful and cautious in trying to understand these processes. So a lot of people have spent a lot of effort in trying to understand all of these processes. It's a lot of observation has gone through. So all of you have seen these things happening, right? You've seen water dripping off of leaves. You've seen water running along the stems, down the stem of the tree and joining the ground. So all of these things you've seen, but it's just that these are the possibilities that can happen. Okay, now obviously all of these different processes that we're talking about are extremely difficult to estimate, to say with confidence that in this particular area, this is the amount of water that will get intercepted, this is the portion of that which will evaporate, this is the portion that will become through fall, this is the portion that will become stem flow. Is very, very difficult. It depends on so many factors. I mean, obviously we can't control which monkey is jumping from which tree to which tree, right? Even something like that can impact the water dripping off. If there were no monkeys, then the water may just slowly evaporate back. But because a monkey jumped from one tree to another, or the wind was blowing, or something happened, and then those drops of water, they actually end up falling on the ground, and they may become part of runoff. So, and if it was only one tree, it wouldn't matter. But if it's hundreds and thousands of trees, then all these drops of water, if you collect them together, it becomes a big quantity, right? So it's very interesting. Okay, very recently, I was actually I was reviewing one of the PhD thesis from IIT Madras, and there was a student who was uh, looking at leaves that are at the top of the tree versus leaves at the bottom of the tree. How the leaves, depending on where they are in the tree, how they differ in terms of the behavior. Okay, he was looking not at a tree but at a crop. Okay, the leaves of the crop that are at the top of the crop and the leaves that are at the bottom, which are in the shade, right? A leaf that is exposed to the sun versus a leaf that is not exposed to the sun, there is a difference in behavior of those leaves. Okay, so what I'm trying to say is, if you get into the details, there's lots of interesting work going on, and each of these different things, there are people writing research articles on each of these things. Okay, so it's very important. Okay, just trying to make that point to you guys. So I mean, at this point, we are only going to describe it. We are not going to try to estimate anything. We are only going to just describe these different processes so that you understand what are the possibilities. Okay, so it's very difficult to estimate. Okay, so it depends on so many things. As I said, it depends on the vegetation type, the density, the type of storm, right? If it's a 15-minute duration storm of high intensity, the interception will be different. If it's a 2-hour storm of very low intensity, the interception will be the characteristics of the interception will be different, and so on, right? So it's a very complicated process. Okay, any questions? Okay, moving on. Depression storage. Now, depression storage, I mean, there's not much to really explain about this, but let's just think about this. Before any runoff can happen, all the depressions that are there on the land surface must be filled. Okay, does this make sense? Because even if some runoff starts to happen, right? So let's just imagine I have land surface like this. Okay, let's say the rain starts to fall here. Okay, so this will get filled up, and then it will overflow and it becomes runoff. It goes here, it comes here, this gets filled up. Only after this gets completely filled, then it starts to overflow. Then it comes here, this place will get filled up with water, and then it overflows. Then this will get filled up, and only when it gets filled up, then it flows out, and then this depression gets filled, and so on, right? Only when all the depressions get filled, then there is no place for the water to go, so then it starts to run off, right? So that's something that's very important, right? Now this depression storage, what happens is that typically, sorry, I'll just erase this. What happens is that there's only two things that can happen to depression storage. It can either infiltrate into the soil or it can evaporate back into the atmosphere, right? So imagine this. I have a little depression in which there is water stored. What can happen to this water? It can either evaporate, sorry, or it can infiltrate. Is there anything else that can happen to it? Is there anything else that can happen to the depression storage? Now, I mean, I don't know how many of you followed the India-England Test series, right? There was a rainfall event, and then there's some water that is stagnant on the outfield. Okay, now that's the only exception to this, right? So most of these grounds these days, they have very sophisticated drainage system, right? So the water infiltrate into the ground, and then it just flows out, so it infiltrates. But even after that, if there is still some water left in the ground, we don't wait for the sun to come and it to evaporate, because you start losing time. So they'll bring a super sopper, some kind of a machine that will come and just suck up all that water and then drain it out later on. That's the only exception. Only on a cricket ground you have anything other than these two things happening. Infiltration and evaporation is what happens in general to any depression storage. Other than that, any other depression where water is collected, these are the only two things that can happen. The water can either infiltrate or it can evaporate back into the atmosphere. No other possibility is there. Okay, all right. Again, so what are the kinds of factors that will affect depression storage? Anybody uh, would like to guess what are the factors that affect depression storage? Nobody wants to guess. Let's call on somebody. Okay. Venkatesh. Oh, there's multiple Venkatesh. Okay, let's say Veera Venkatesh. Okay, nobody wants.
Hello, sir.
Yeah, go ahead.
Hello, sir.
Go ahead. Go
Can
ahead.
you repeat the question? Uh,
What,
I have
what,
internet broken.
no problem. What are the factors that affect depression storage?
It depends on the intensity of the rainfall.
Depends on the intensity of rainfall. Okay. Okay.
Yeah.
Anything else? You said something else. Say that again.
Depends on different stuff, like how it is, how much seepage going through that particular
So
place.
basically, the type of soil you mean.
That's all.
Okay. Thank you. Audio is not very clear. We'll leave it there. Okay. So it depends on the type of soil, of course, right? It also depends on the condition of the surface. If I don't have too many depressions, or if my depressions are limited in number or small in number, then I'll have less depression storage. So for which is why when they, for example, when you make a ground, you make the ground with a gentle slope, right? You try to make it without having too many depressions, because if you have a depression, then there'll be water stagnation and so on. If you have a gentle slope, if the condition of the surface is maintained properly, then the water drains off instead of collecting in one place and creating stagnant water. Now, it also depends on what kind of rainfall happened before. That's what's called antecedent precipitation, right? So let us say today I'm having rainfall of 1 centimeter, okay? But yesterday, suppose I received 5 centimeters of rainfall. Suppose I received, let's say, suppose I received 2 centimeters or 3 centimeters of rainfall yesterday, okay? And then now today I'm receiving another additional 1 centimeter of rainfall. Will this 1 centimeter of rainfall contribute to depression storage? Yes, no. Will it contribute to depression storage? If I received 5 centimeters of rainfall yesterday, and then today I receive another 1 centimeter of rainfall, will today's rainfall add anything to depression storage? Yesterday's rainfall will already, the depressions will already be will be full. So today's rainfall will not add anything to that, right? Because between yesterday and today, there's not enough time for evaporation to happen. There's not enough time for a lot of infiltration to happen because I received 5 centimeters of rainfall, right? So if I that's what I mean by antecedent. Antecedent means what happened previously. Previous day's precipitation or previous 1 hour or 5 hours or whatever, previous precipitation that happened will impact how much depression storage will happen for today's event or for the current events, right? So that's also an important factor. Again, very difficult to estimate exactly and with a lot of confidence how much depression storage will happen. So it's a very complicated topic again. Okay, so depression storage is again a slightly difficult parameter to estimate, right? How much water will actually get stored in the form of these depression storage is something that is very difficult to estimate. Okay, any questions before we move on? Okay, so let's move on to the third abstraction. which on this we'll be spending quite a significant amount of time. And this one, as I said, is referred to as the major abstraction, right? So basically, what is infiltration? It is the flow of water into the soil, as simple a definition as possible, right? I have some water falling on the land surface in the form of precipitation. Now, that water may not necessarily just flow on the surface, it may flow into the soil. Now, that process, I just simply call it infiltration. Of course, different people will call it percolation, seepage, recharge, lots of different words are used, but infiltration is the most commonly used and the most, how do I say, most well represented term, right? Seepage has slightly different shades of meaning. Recharge also has slightly different shades of meaning. Infiltration or percolation, these two words seem to be the most precise way of explaining this particular phenomenon of flow of water into the soil. Okay, so what it's doing, it's converting surface water that was above the surface of the land. When it falls, instantaneously it is above the land surface, but once it enters into the soil, it is no longer surface water, it has become subsurface water, right? So the word subsurface indicates that it is below the surface, right? Below land surface. When I say surface, I mean land surface. Okay, so that's why when you have uh, uh, a metro train that goes underground, you call it a subway, right? Or you have anything submarine is something that goes under the surface. So the prefix sub is used to indicate something that is below, right? So infiltration, what it's doing is it's converting surface water into subsurface water, right? Which is another way of saying groundwater, okay, underground water. Okay, now the subsurface water, uh, uh, it actually occupies two zones under the land surface. One zone is referred to as the unsaturated zone, where some of the voids are filled with water, and then naturally you can expect what the other zone will be called. The other zone is called the saturated zone, where all the voids are filled with water, right? So when I look at uh, soil under the land surface, there are two broad categories of zones of soil with respect to the water content. One is the unsaturated zone, where the voids that are present between the soil particles, some of those voids are filled with water, and the saturated zone in which all the voids are filled with water. That's it, right? That's the only distinction between subsurface water that's present in the unsaturated zone and that is present in the saturated zone. Now, if I'll just draw a picture of this. So let's say this is my land surface, okay, and then I'm going to draw some demarcating line here, okay. This portion above this dotted line, I will call it the unsaturated zone. Okay, what that means is that if I have some soil particles, I'm just drawing them, I'm exaggerating the size and drawing them very big. Okay, if I have some soil particles like this, then in the unsaturated zone, some of these voids that are present between the different soil particles are going to be filled with water. Okay, so what that means is maybe there's a little bit of water here, maybe there's a little bit of water here, maybe there's a little bit of water here, and so on. Okay, the entire void is not filled. Okay, and that is the portion above this dotted line. Okay, below the dotted line is what we refer to as the saturated zone. And as I said, the simple way to think about it is that if I have multiple soil particles here, all the voids between those particles of soil are completely filled with water, and so therefore it's referred to as the unsaturated zone. Now this dividing line, that dotted line that I've drawn, which demarcates the saturated zone from the unsaturated zone, what do you think that is called? What do you think that is called? This dotted line over here is referred to as the water table. Okay, so that dotted line that I've drawn over there is referred to as the water table. So which is, you must have heard people say the water table is 10 feet below the land surface, right? What they mean is that up to a depth of 10 feet, the voids are not completely filled. Below the depth of 10 feet at that particular location, the voids are completely filled with water. And so therefore, if I drill a well there, I will find that there is water present below the depth of 10 feet. Above the depth of 10 feet, my soil may be wet, but it is not completely saturated. It may have a little bit of water in it, right? Depending on the nature of the soil and so on and so forth. But the water table is basically the point, the dividing line between these two zones. Okay. All right. So this, yeah, so that's what I was trying to tell you. So the surface below which the saturated zone exists is called the water table. And the water table, interestingly, is supposed to be at atmospheric pressure, right? So if you look at this water table, the pressure at this point is P atm. Okay. And if you go below the water table, what will happen to the pressure? Let's say I pick a point here below the water table. What will the pressure here be? Will it be equal to atmospheric pressure, or more than atmospheric pressure, or less than atmospheric pressure? What do you think? So there's only three options. It is equal to atmospheric pressure, more than atmospheric pressure, less than atmospheric pressure. Anyone? Quickly. Sindhu. Okay, no response. All right. So if you pick a point below the water table, the pressure will be greater than atmospheric pressure. By how much? Depends on the height, right? If this point is at a height of h below the below the water table, the pressure there will be P atmospheric plus rho GH. You're already familiar with this. It's the hydrostatic pressure distribution, right? So the hydrostatic pressure distribution is assumed to exist even below the water table. It's supposed to increase linearly with H. As H increases, the pressure keeps increasing above the atmospheric pressure. Okay, and then of course, if you get rid of the atmospheric pressure, you can write, now if you write it like this, it's the absolute pressure. If you just remove the atmospheric pressure, then it will be called the gauge pressure and so on. Okay, all right. So I don't know if I have time for this. Let's just quickly wrap up. Soil moisture. Now, soil moisture is one of the ways in which we distinguish between a sample that is in the unsaturated zone versus a sample that is in the saturated zone, right? So, if my soil is completely saturated, then it will be in the saturated zone, and if it is not completely saturated, then that's soil sample is supposed to be present in the unsaturated zone. Now, whenever you have an unsaturated soil sample, you can use soil moisture as a way of estimating what is the extent to which this particular soil sample is saturated. Okay, so the way we use this is by you're all familiar with this, right? So we define two terms. One is the porosity. I use the letter n, small n, to refer to porosity. This might be the same thing that you use in your geotechnical engineering also, small n, to refer to porosity, which is simply the volume of voids divided by the total volume of the sample, right? So that's one parameter that I used to describe soil moisture, right? Then the other parameter that I use to refer to soil moisture is what is called the moisture content. Okay, and for this I use the Greek letter theta. Theta is the moisture content, which is given as the volume of water divided by the total volume of the soil sample. Okay, so now what is the range of values that theta can take, given that this is my definition? So theta will go between what and what? What is the lowest value that theta can take? If my soil is completely dry, then what will theta be? Anyone, quickly? I'll stop with this. If my soil is perfectly dry, theta will be 0, right? This is a dry sample. And if my soil is perfectly saturated, theta will be it will be equal to porosity n, because then a perfectly saturated sample, the volume of water must be equal to volume of voids. So these two, theta will become equal to n if the sample is fully saturated. Okay, and if it's completely dry, then my theta value will be 0. Okay, so I'll stop with that for now, and we will not be having our Friday class because it's Independence Day. Happy Independence Day, everybody. I'll keep you posted. I might record one lecture and then upload it for you to watch over the weekend. Okay, or we'll take it from there. Okay, I'll keep you posted. Okay, I should be back by Monday for your next class. In case I'm not able to make it on Monday, we'll see. I'll send an email. Okay, most likely I should be back. Okay, all right. Take care, everybody. Happy Independence Day, and see you all soon. Bye bye.